So we can now link our angular acceleration and the equations for angular motion to our equations for linear motion. So this is what we know. We know that, displacement is equal to r times theta. That's arc length. And from that, we got that linear velocity is equal to r times omega. We got that linear acceleration is equal to r times alpha. And so it's a one-to-one correspondence between angular and linear equations of motion. So everything is just different by a factor of r. And what ends up happening is, if we were to go and derive all of our new equations of motion, keeping with our standard definitions that theta is equal to angular displacement, omega is equal to angular velocity, and alpha is equal to angular acceleration, we have this great correspondence, which you'll see here. So our first linear equation from kinematics was that d is equal to 1/2 v1 plus v2 times time. And the the angular corresponding formula to that is that theta is equal to 1/2 omega 2 plus omega 1 times time. Very similar for acceleration equals v2 minus v1 over t. Alpha is equal to omega 2 minus omega 1 over t. D equals v1t plus 1/2 at squared. And of course you can now predict theta is equal to omega 1t plus 1/2 alpha t squared. Got this equation as well. And finally, the last equation, v2 squared equals v1 squared plus 2ad. Same thing. Omega 2 squared equals omega 1 squared plus 2 alpha times theta. And so those are now angular equations of motion. Very easy to prove. We're not going to do it here, but you can do it. Remember from mathematics that our convention for angular direction is standard. If we go counterclockwise, that's said to be moving in a positive direction. Clockwise is said to be moving in the negative direction. So here's example 3. A flywheel at rest undergoes an angular acceleration of 5 radians per second squared for 10 seconds. What's the final angular velocity? We know alpha. We know what omega 1 is. It's equal to 0. We know the time is 10 seconds. So what's omega 2? So we'll use this formula right here. It's one of the 5 that we just looked at. Sub in our values, and we can see that omega 2 is equal to 50 radians per second. And that's the final angular velocity. So we're using this in a very similar way as we've used kinematics. And you'll see the same type of thing coming up again. A disk initially rotating at 2 revolutions per minute accelerates at -6 radians per second squared, so in the opposite direction, for 20 seconds. What's its final angular velocity? So this is what we know. We know omega 1, we know alpha, we know t, and we're trying to find omega 2. But a little hitch in the road here is that omega 1 is equal to 2 RPMs. RPMs is revolutions per minute. We need radians per second. So we need to do a quick unit conversion. 2 RPM is equal to 2 revolutions per minute. In every revolution there are 2 pi radians. And in every minute there are 60 seconds. And when we do this, we get pi by 15 radians per second is the first, or the initial angular velocity. So we can now turn to this equation, omega 2 equals omega 1 plus alpha t. Sub in our variables, and we end up with a negative omega 2. And of course what that means then is that because it was initially rotating at 2 RPMs in a counterclockwise fashion, now we have a negative angular velocity, which means it's simply rotating the other way. So it's rotating clockwise. The final angular velocity is 120 radians per second clockwise. Final example. A disk initially rotating at 100 radians per second is stopped by a force which acts for 25 seconds. Through what angle did the disk rotate during this time? And what was the angular acceleration of the disk during this time? So the important thing is that it stopped. So omega 2 is equal to 0, while omega 1 is equal to 100. So we can use this equation here to discover that alpha is going to be negative, of course, because if it's rotating at 100 radians per second in the counterclockwise direction, if it comes to stop, then that means it must have an angular acceleration, which is in the clockwise direction. And of course, we can also calculate the angle through which it rotates. Of course, it'll go around several times before it stops. And we can calculate how many times it actually goes around, or how many radians through which it rotates. That's 1250. And those are the basics of angular motion.